Welcome back for our last discussion in volume, where we're going to wrap things up in the volume section in 7.3 with talking about a slightly different way to calculate volume that may be advantageous to us depending on the setup that we are given. So the idea of calculating volume is still going to be the same. Nothing's changing about the method. We will still be drawing our region, understanding our region, knowing our axis. We will still be taking a cross-section. We will still be revolving that cross-section and then integrating those areas together. The only difference is one subtle change is the main point today is we will be taking cross-sections parallel to the axis of rotation. So cross-sections parallel. So that means in the same direction as the axis of rotation. That is the main difference. And so we're going to go back and revisit a problem that we did in the last discussion. And instead of taking cross-sections perpendicular to the axis of rotation, giving me discs or washers, and remember this example required quite a bit of work. We had to set up two different integrals because we had two different shapes. We had discs and washers depending on where we were. And we had to change dependencies in terms of y because we had to take horizontal cuts. I'm going to take the same exact region and the same exact axis. I'm not changing the setup of the problem. I'm just going to change the way I take my cross sections. And so if we draw this region out again, just like we did before, and don't worry, it's not to scale. Our region looks something like this. Bounded in the x direction by 1 and 3, below by the x-axis, and above by the curve 1 over x. At 1, 1 over x is 1. At 3, 1 over x is 1/3, giving me this bounded region. And then we revolve this region again about the line x equals 3. So a vertical line at 3. And when we took the axis rotation at x equals 3, a vertical line, we required our cuts to be perpendicular, so horizontal. And that's what created the problem, right? We had discs between 0 and 1/3 in the y direction. After 1/3, between 1/3 and 1, if we take cross sections, we're going to get washers, creating two different formulas to calculate, two different integrals to set up and evaluate. And so to bypass all of that, what we're going to do now is make a subtle change. We're going to generate a new type of shape by, instead of taking cross sections perpendicular, parallel to the axis of rotation. And we're going to see it's going to not generate a washer or disc anymore, it's generate a new type of object, and we'll discuss what that is. And so let's take a cross-section parallel to the axis of rotation. So now my axis is vertical, meaning now I make a vertical cut. Now we're back to an x dependency. That means I don't need to change any of these functions. I will use the bounds from 1 to 3 instead of 0 to 1, 0 to 1/3, and 1/3 to 1. And so instead of having those bounds, we have our x bounds from 1 to 3, parallel to the axis of rotation, make that cut, x dependency, everything's already set up for me and done. And then we will rotate or revolve that cross section about this line. Now, in this case, be careful, we revolve this straight line about that green dotted line. It generates a different type of object for me. In this case, it does not generate a disc. It does not generate a washer. It generates a new type of shape. It's a hollow cylinder. It's just a piece of paper, right? There's nothing filled in, right? I could stick my hand through this if I needed to. It is a rolled piece of paper, right? I could see through it, a telescope or something. In fact, in general, we call these types of shapes cylindrical shells. Shell because it's just the outside of it. And cylindrical shell, but in general, we're just going to call it shells, and then how you use the shell method. And so before we go to calculate the area, let's go ahead and remind ourselves, well, what would the area of a cylindrical shell be? Remember, it's not the volume of a cylinder, it's the area of a shell, right? This is hollow, right? There's nothing inside of the cylinder. Well, if we go back to geometry, we still need a couple things. We need the radius and the height. Remember, it's not the area of the circle times the height because there's nothing in this shell. It's hollow. We just need the circumference of the circle, which is 2 pi r. That's the circumference of a circle times the height. And so the circumference times the height will give me the area of the shell of this cylinder, circumference times height. And that is how we will find the area of these shells in this. We would need to measure the radius and the height of each shell. Once we know the area of the shells, we will integrate them together, right? It's just a different shape. So nothing's changing about the process. We still know our region, we know our axis. We make a cut, a slice, in this case parallel to the axis of rotation, determining my dependency and all that kind of fun stuff. We revolve that cut, that slice that's parallel, now generating a new shape, a shell. We find the area of the shell, and we integrate those shells together. And so let's go ahead and find the area of the shell. So we get a shell in this case. What is the area of the shell? Well, we would need to know 2 pi r times h. We need to know r and h. Now again, everything's in the x variable, so we need to make sure everything's in x. Let's go ahead and find the height. The height is something we could do even back at the beginning of chapter 7. The height would just be the length of this vertical line, the height of this shell. Well, that's just the distance between these 2 points in terms of x. Well, that would be top curve is 1 over x, bottom curve is 0. So 1 over x minus 0, that's the height. So that's not too much work. That's something we could do from chapter 7.1, distance between 2 points. So the height is 1 over x. Now, the radius, interestingly enough, the radius then is the distance from the center to the edge. Now, the center is still at 3, so 3 is going to be important. It's going to be in this calculation because it's the distance from the center to the edge. And the center is in front of the edge, right? The edge is here. And so it's going to be 3 minus something. The distance from the center to the edge. 3 minus, right? So 3 is the center. It's in front of the edge. 3 minus. Now, the edge of this cylinder in no way depends on the curves, right? It doesn't matter how big this line is. It's just a vertical line. And it has nothing to do with 1 over x or 0. In fact, it's a vertical line at wherever you chose x to be, at just x. If x is 2, it's 3 minus 2. If x is 1.5, it's 3 minus 1.5. If x is 2.5, it's 3 minus 2.5. It's that constant. And so in general, it's just 3 minus x. It has nothing to do with the curves. In general, when we use the shell method, when we calculate the radius using shells, the radius never depends on the curves. The heights depend on the curves. But the radius doesn't. The radius is the distance from the center, which depends on the axis, to the edge. Now, the edge is just going to be either at x or at y, depending on which way you're making your cut. And so we have the radius and we have the edge. And so now we put it together, or we have the radius and the height. We put it together. We get 2 pi r times h. Let's go ahead and distribute this out. Let's simplify this formula first. This time, so we get 2 pi. If I distribute the 1 over x, we get 3 over x minus 1. So 2 pi, 3 over x minus 1. And then what we're going to be doing is we will now take this formula and add up all those shells together, just like we did with discs or washers. And so now we're going to integrate or add up the areas of all of these cylindrical shells. As I move along the x-axis now, right, we're making x dependencies from 1 to 3 using my x bounds. Now the 2 pi can be pulled out. Using my fundamental theorem of calculus, again, remember 3 over x, antiderivative is ln. So we're going to get 2 pi times 3 ln of the absolute value of x minus antiderivative of 1 is x. Remember, antiderivative, not derivatives. So antiderivative of 1 is x. And then we're going to take that antiderivative and evaluate at these points 1 and 3, subtracting them appropriately. And so what do we get? We get 2 pi times 3 ln of the absolute value of 3 minus 3. And then minus plugging in 1. So plugging in 1, we get 2 pi times, let's change my parentheses a little bit here. that so we see it clearly. So 2 pi times, plugging in 1, we get 3 ln of 1 minus 1. Let's clean this up a little bit to see what we get. So here we get 6 pi ln of 3. Okay, what do we get? We get minus 6 pi, right, when I distribute the 2. And then what do we get here? We get 3 times ln of 1. Well, that's 0 because ln of 1 is 0. And then distributing the 2, we get negative 2 pi, but then negative again gives me plus 2 pi. And so if we look at the answer, we get negative 6 pi plus 2 pi is negative 4 pi plus 6 pi ln of 3. Now, this answer should look somewhat familiar because if you remember, we did the same exact region, the same exact axis, and we calculated it using discs or washers. Now, since it's the same region and the same axis, nothing's changing about the shape I'm generating. The only thing that's changing is how I calculate that volume. When we use discs and washers, we took cross-sections perpendicular and add them up. Here we're taking cross-sections parallel and adding them up. We get the same solid at the end of the day, and so this number should be the same. If you look back at the last discussion, the last video, you'll see that, hey, well, this looks a little bit different. We have the negative 4 pi, but then remember we had minus 6 pi ln of 1/3. Well, they're the same number, so I'm just going to show you this really quick, but they are indeed the same. How will I do that? I'll use a property of logs. And so plus 6 pi ln of, I'm going to write this as 1/3 to the negative 1 power. Why would I do that? Because I want to relate it to 1/3. Because if I take the reciprocal 1/3 to the negative 1 power, that's 3, right? Negative exponents just mean reciprocals. And so 1/3 to the negative 1 is 3. I'm just rewriting it kind of silly. And that's because I want to show something. And then the property of log says, why do I do that though? Property of log says I can take that exponent and write it as a coefficient. So I bring that negative 1 down, and now we see this is indeed the same answer we got in the last one, where we said, oh wait, it looks scary because I think it's negative, but it's actually not, right? This was my answer, and it's the same as the answer we got before. So nothing's changing about the volume we're calculating, just the method in which we do it. Nothing changes about the process, just the shape that we get. And so this is the last method, shells. The only difference in the process map is we take slices parallel to the axis and generate a new shape called a shell. And as long as we can measure the area of those shells, which we can, we would go about it in the same exact way. And so what we'll do is we'll finish up with one more example using shells just to reemphasize this idea. And we'll go back to an example that we did before that was easier with washers. That's now going to be a little bit harder with shells, but we can still do it. And so let's go back and do one more example in which we will use the washer method one more time with a different example. And so consider the region bounded by y equals x, y equals the square root of x, revolve the region about the line y equals 2 and find the volume. Now this was an example we did before when we did washers and discs. I'm going to take the same exact thing, same exact region. So I'm just going to redraw it again. Square root of x is the function on top, x is the function on bottom, revolving around the line y equals 2. And finding the volume. So I draw my region, I know my region, I know my axis of rotation, I want to find the volume, and just to reemphasize shells, we will again take cross sections parallel to the axis of rotation. Now, in general, I wouldn't want to do this because I don't have to change my dependencies, but we'll do it nonetheless. And so I'll take cross sections parallel to the axis of rotation. That means I need to take a horizontal slice. Horizontal slice now means everything needs to be in the y dependency. That means I need to go back over here and rewrite these as functions of y. The first one is just x equals y. The second one, we would need to square both sides and get x equals y squared. These are the versions of the functions I need to use. And so this one was x equals y squared. This is x equals y. And I use my y bounds of 0 to 1. And so we revolve that cross-section. So now that I take my cross-section, I know my dependency, I change anything if necessary, which we needed to. I revolve that cross-section about my axis of rotation, and of course, it generates this new shape, this shell shape. To measure the area of the shell that we get, we would need to know the radius and the height, and 2 pi r times h would be the area. Again, the radius is the distance from the axis of rotation to the edge, and the height would be the length of that line, right? And so we need r and h. Let's go ahead and measure h first. That's the easier one. H would be the length of this blue line. That's the distance between these two curves. Subtracting in the right way would be the bigger one is this curve, which is x equals y. The smaller value is this point, which lies on the curve x equals y squared. And so we would need to write it as y minus y squared. Y minus y squared. Now to find the radius, that would be the distance from the center, which is at 2, to the edge, which is at a generic y value, so at y. Has nothing to do with the curves again. Subtract in the right order, the axis of rotation is bigger, so 2 minus y. 2 minus y is the radius. Finding the area of the shell now is 2 pi times r times h. 2 pi r h. And let's go ahead and FOIL this out before we write the integral just to clean up a little bit. So we get 2 pi. FOILing this out, we get 2y minus 2y squared minus y squared plus y cubed. And let's go ahead and combine the y squareds. And so now finally we get a washer formula. I leave the 2 pi out because we're going to pull it out of the integral anyway. We get, writing the bigger term first, y cubed. My y squared terms is minus 3y squared. And then plus 2y. That's the area of the washers, or sorry, the area of the shells. I'm going to add them all together, integrate them in the y bounds from y from 0 to 1 as we move along the y-axis. And now we have a definite integral to calculate. Remember, at this point, we haven't learned new techniques of integration. That's going to come in chapter 8 in future discussions. And so right now, once we have the setup correct, we should be able to answer the definite integral using everything we know from Calc 1. So, i.e., you can calculate using power rule, like we've done so far. Worst case scenario, use substitution, right? Use substitution may come up. So don't forget that technique. Now, in this case, let's go ahead and factor out the 2 pi, because it's a constant. Y cubed minus 3y squared plus 2y. And using my power rule on all of these gives me an antiderivative. 1/4 y to the 4th minus, well, just y cubed, which is nice, plus just y squared, which is nice. And I evaluate this from 0 to 1. And now we plug it in. So we get 2 pi. Plugging in 1, we get 1/4 minus 1 plus 1 minus 2 pi times 0. Okay, so that term's gone. The 1's cancel here, leaving me with 2 pi times 1/4, which is pi over 2, 1/2 pi, which is the same answer we got before using the discs or washer method. The only difference, of course, now is we use shells. Nothing's changing about my region or my axis, so of course we should be getting the same volume again. The only difference is the method in which I calculated that volume. Here I took cross sections parallel to the axis of rotation, generating shells for me, but the idea is still the same. And so the way we calculate volume using calculus is, again, this idea of infinitesimals. If I know something about the infinitely small, the infinitesimal, right, this cross section, revolving only that infinitesimal piece, I can then say something about the whole via integration, right, making the many infinitesimal pieces one solid object. And that's the beauty of calculus. It allows me to find volumes of solids of revolution. And so that will end our discussion on volume. In the future discussions, we'll continue with applications of integration, and we'll apply it to other examples like measuring the length of a curve or surface area, as well as a physics example. We'll look at work, for example. Other than that, hope that was helpful, and I'll be talking to you all soon.